Yes.
For most of my lifetime, I was expecting a big bang, an expanding universe, and as you say, with increasing entropy going on. But if the second half of that cycle had a big crunch coming, and the universe started to contract, would entropy decrease in that second half, and does that violate any of your principles?
So so the question. By the way, I'm totally off mic here. Are we still good on the back?
Yeah.
Yes.
So the question is, and by the way, I was most of the way through graduate school before we knew the universe was accelerating, and I lived most of my education on the knife's edge, not knowing whether the universe would contract or expand forever. But so the question was, there used to be, and it seems to not be the case anymore, that our universe might have just enough stuff in it to stop the expansion and cause it to collapse. Now, think about a universe that's filled full of stuff. The entropy gets larger and larger. The entropy gets greater and greater and greater and greater. And imagine we've got a completely smooth distribution of stuff. And now the whole universe collapses and gets back to a state that looks very much like the Big Bang. Doesn't that mean we've gone to low entropy again? Yes. Yes, that's exactly what it means. And so this is something that people have speculated on a lot, right? And this is why it makes the question about the arrow of time so significant. Because imagine that had been the case. And this is something that Hawking, speculated on. It's like, well, could it be the case that if the universe starts collapsing, that effectively we're now going backwards in time? Like you only remember up to when the universe turns around, because then after all, once it's turned around, you're essentially going backwards in time. You don't ever feel yourself going backwards in time. It's just you only go up to that point.
Well, so, I was going to exclude life forms and intelligence.
Yeah,
because they're a phenomenon of localized entropy reduction.
They're localized entropy reduction, but again, we've still got the same basic question. I actually have a big problem with the idea that the arrow of time is defined by, I didn't want to get too much into it in the talk, but it's defined by the overall flow of entropy. For the simple for examples like that, but also because there's no mechanism in the universe, there's no other physical phenomena that ever care about anything that isn't local. Like when we ever do calculations, they're always based on whatever quantity, temperature, charge, whatever, is in a particular region, and how much flows in and how much flows out. We never care about some global number, and yet somehow the arrow of time is supposed to know about the total amount of entropy in the universe at any given instant. Well, that seems kind of arbitrary. How does it know? That's my 2-second criticism. Yes.
One of the techniques used to establish for sure that the laws of physics are equivalent in every part of the universe. Is it just a mathematical proof, or is there any way to prove absolutely that is the case?
So I mentioned so the question is, how do we know that the laws of physics are the same everywhere in space or in time or whatever? So there are ways we can approach these things. In time, I mentioned the Oplo experiment, but in space, one of the big experiments that people have done, this talks about both space and time, by the way, is to look for variations in what's known as the fine structure constant. So the fine structure constant is basically a combination of the charge of the electron, Planck's constant, which is sort of the number that goes into quantum mechanics, and the speed of light. And it's a number that's sort of just hardwired into our calculations of things like how the hydrogen atom and other atoms work, and what the energies of the photons that come out of these things are. And so you can make a prediction, you can do a calculation. And so I can look at particular objects, and I forget the spectral lines we look at. We can look at objects in one part of the sky, and look at objects in another part of the sky, and look at the ratios of their various photons, their energies that are coming off the photons, the lines. And you could say, is this a fixed ratio, or is it something that seems to vary with orientation? And there have been groups, there's been a group, that has said, oh no, we see an actual signal, that part of the sky, and seems to have a difference by about 1 part in 1,000 or something like that. Significant, they claim statistically significant measurement. difference between the fine structure constant in that part of the sky and that part of the sky. Every other experiment that has been done that tries to see the same thing doesn't. But yeah, no, you're absolutely right. You can't just do it purely theoretically. Now there is, I will say, there is a sort of theoretical basis. Cosmologists have this thing we call the cosmological principle, which is basically, wherever you go, there you are. We assume that the laws of physics are the same everywhere, and the universe is statistically the same, on average the same, in every point in space and in every direction. But you have to have some, only because we have one universe to look at, right? So we have a limited amount of knowledge. But we do try to back that up whenever possible. I think that's a question.
Yeah, you were talking about the properties of antimatter, and I was just wondering if you knew anything about the I guess, proposition that antimatter flows against gravity as opposed to the way that normal matter does, and the efforts of CERN to sort of prove that.
Yeah, so actually I wrote an IO9 column on this question, does antimatter have anti-gravity? The problem is that, the error bar, we assume that antimatter has normal, I was going to draw error bars, just as I remembered them, but we assume that antimatter has normal gravity. Everything we've ever seen, our assumptions about how gravity works are based on the idea that antimatter has normal gravity. But this is also something we can check. The problem is that currently the error bars are something like 5 times larger than the signal. So it's consistent with all of the following. Exactly the same as ordinary matter, no gravity at all, and the opposite of gravity.
It's just a matter of looking at it.
It's a matter of reducing the error bars at this point. The error bars are gargantuan. It's tough because you're talking about the gravity on like an individual atom, or anti-atom. Very tough. Yes.
How does the antimatter relate, say, to dark matter? And then how's it anti-dark matter and anti-dark?
It depends. Okay, so how does antimatter relate to dark matter? As near as we can tell, it doesn't. Probably, possibly. It depends very, very strongly on what dark matter is. So first of all, antimatter is a catch. We think of it as a catch-all term, but there are particles that are their own antiparticles. Light, photons, is its own antiparticle. The Higgs, there is no anti-Higgs. The anti-Higgs is the Higgs, is its own antiparticle. So we've got this. I mentioned this idea that unfortunately data is suggesting is quite possibly wrong of supersymmetry. That is to say, there's 2 different main types of particles called bosons and fermions, and the idea is that for every boson, there's a fermion, and for every fermion, there's a boson. Sounds very similar to antimatter, but it's not. It's not the same thing as charge. It's not. The masses can be quite different, and so on. And so, if this were correct, there's a particle, which is typically called a neutralino, or a lightest supersymmetric particle, that is predicted to come out of this. And I believe it's the case, if I'm wrong on this, I apologize, but I believe it is the case that a neutralino happens to be its own antiparticle, that there is no other variant of that. So, it would happen not to be the case. Now, the fact is we don't know what dark matter is, so it may be that antiparticles are somehow related to dark matter. I will say one very important thing, which is that dark matter is pretty much by definition electrically neutral. Because if it wasn't electrically neutral, there'd be, it would interact with light, and it wouldn't be dark. High definition. Why don't we take 1 or 2 more, and then that way we can break for signing and other questions you guys may have. Yes.
Yeah, I guess this is more of an astronomy type question, but I've always been curious to see, you can look at a star chart, and this is the universe as we see it. I've always been curious to look at a star chart that shows the universe as it is, considering the fact that everything that we look at is actually much older than what it really is. It's in a different position. Are there any efforts to create like a as the universe is star chart?
Well, okay, so see, you're assuming that now has some sort of meaning. Einstein says you're full of it. There's no absolute now. Now that said, I know exactly what you mean. Right.
Yeah.
I look at Alpha Centauri.
Project where it's supposed to be.
Yeah, exactly.
Yeah.
It's 4.3 light years away. You know, okay, if it's 4.3 light years away, I can measure what's called proper motion. You can actually deproject that. So you could, but the reality is, of course, we're talking about differences of arc seconds, less than the resolution of your eye. And you know, we are obviously, whenever we look at anything, we're looking into the past. I mean, you're a few nanoseconds. What I'm seeing right now is a few nanoseconds ago of your face, not your face as it is now. So I mean, we're always looking to the past, but on a galactic scale, and most of the stuff when we do stargazing is on a galactic or solar system scale. We're talking, in solar system, we're talking hours at most. Even on a galactic scale, we're talking at most, even through a fairly powerful telescope, we're talking about thousands of years, which compared to the age of the universe, compared even to the orbital period of our galaxy, is nothing. May as well be instantaneous. So you're right, you're absolutely right. Like you could try to correct, you could make a map like that, but it wouldn't look that different than, because
Really?
These distances are so small comparatively speaking, they wouldn't look that different than they are now. And of course there's some things we can't know because you can't just linearly interpolate, right? Like it's a moving target. How about one more? Yes?
Is there a concept of anti-field? You already said that there's no anti-Higgs field, but fields in general. What happens, for an electromagnetic field? Like if the field, the electromagnetic field can be particles too. What if it was an you said there are anti-photons, right?
No, the antiphoton is a photon.
Is a photon. So it is possible for matter and antimatter to interact with each other without destruction.
Oh, sure. I mean, we think of that as the most reasonable thing to happen. A particle and antiparticle can annihilate and destroy one another. But it's true. Photons obviously hit one another all the time without annihilating. And in that case, it's just because they're not energetic enough. In the early universe, on the other hand, photons were so energetic, it was so hot that they would strike one another and they would create particles and antiparticles basically from scratch. They would effectively annihilate and create new particles. So it's a function of energy, it's a function of how close they connect to one another. You could get them close. What counts as touching obviously is a function of energy and what you're talking about, what type of particle interaction you're talking about. So, well, thank you again.